Guys, this is it. Last section for chapter 7. We've talked a lot about networks and trees, as well as minimum and maximum spanning trees. It's now time to see what we can actually do in order to find a minimum spanning tree, with the assumption that if you wanted to find a maximum spanning tree, you would do something very similar. In fact, we actually have an algorithm for it. It's called Kruskal's algorithm. And actually, it's pretty easy to use compared to a lot of some of the other ones. Probably the closest comparison to what we would have seen in Chapter 6 would have been the cheapest link algorithm. In fact, it's almost identical. In fact, you're going to build it kind of one section at a time, choosing the cheapest possible edge, except we're going to take off one of the restrictions. You can actually have more than two edges coming out of a single vertex. So having three or more edges is actually okay now. But what's different, or what's still the same, is that you don't want to find a circuit. So again, the only restriction that we are keeping from cheapest link, if you remember that from chapter 6, is that we should never ever choose an edge that creates a circuit. But it's now okay to have three or more edges coming out of a single vertex. So just kind of keep that in mind as we look at this. So let's go back to the example that we actually started this chapter with, this Amazonian cable network, and let's see if we can find an optimal fiber optic cable network which connects the towns using Kruskal's algorithm. You might remember this is what that graph looks like when you add the weights to each of the edges. In fact, I'm going to go ahead and show you Kruskal's algorithm, whereas the following slides would talk you through it, so if you want to go back and read them later, you can. All right, so looking at our graph, we look for where is our cheapest possible link. In this case, that would be this length right here from G to F, which has a weight of 42. So that's going to be the first one that we will use, will be right there. Our next cheapest would be connecting B to D at a cost of $45 million. So we'll go ahead and connect those two as well. Our next cheapest would be 49, so we will go ahead and connect that A and D right here. Our next cheapest is 51. However, while there are two options for 51, only one is going to be viable for us. We can't use this 51 that connects A and B because that would create a circuit between A, B, and D. However, we can use this 51 which connects D and G. And now we have actually already 5 out of our 6 vertices connected to one another. Continuing now, we look for our next cheapest link. In this case, it would have to be the 53 between D and C. At this point, D now has 4 different edges coming out of it. That would not work in chapter 6 if we were trying to use the cheapest link to find a Hamilton circuit. However, it does work in trying to find a minimum spanning tree. From there, our next cheapest would be 55. However, we won't be able to use that because it would create a circuit between B, C, and D. Our next cheapest after 55 would be 56, but once again, we're not going to be able to use it because that would create a circuit between C, F, G, and D. So our next cheapest is 59. That is in fact what we will want to use. That will connect C to E. In fact, we now have all of our vertices connected. We can now calculate the cost, which would be 45 plus 49 plus 51 plus 53 plus 59 plus, I think I forgot the 42 there. Should be, let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Add these together. Let's see what we get. I know these combine to be 100. These combine to be 95, so that's 195 plus this one is 240. I think and then going to end up with 299 as the total cost for building this network. Now, what you might also want to do is actually redraw that a little bit better so you can see how everything is going to be connected. Pretty easy to do that. All you do is just draw in the paths that you are planning to keep. So you would have, let's see, A to D. You have D and B connected. You also have D and C connected. C is connected to E. D is also connected down here to G. And G is connected right here to F. So here would be our minimum spanning tree, which you can see how that fits onto our network. And there you've got our cost for that minimum spanning tree. So again, the next couple of slides will just kind of talk you through everything I just showed you. So I'm going to go ahead and skip over those. And we'll just check to make sure I did the mental math correctly. And it looks like I did. There is that same cost of $299 million that I mentioned. And again, here is that spanning tree, so you can see what that looks like. Again, they've just gone through and removed the extra edges. So here is what you should probably write down for Kruskal's algorithm. This would be your step-by-step for how to do it. Step number one, you're going to start by picking the cheapest link possible. If it's a tie, then you just pick one at random. Step number two, pick the next cheapest link and mark it. And then in steps 3, 4, and so on, you're just going to continue picking and marking the cheapest link that's possible as long as it doesn't make a circuit. If it makes a circuit, cross it off and look for the next cheapest. Once all of your, and then again, to finish the algorithm, obviously once you've connected all of your vertices, then you're done and you have your minimum spanning tree. Now, if you instead wanted to find a maximum spanning tree, which we don't really look at those as often, most of the time we want to minimize the cost, but maybe you wanted to maximize it for some reason. Instead of picking the cheapest link, the only thing instead that you would do is change cheapest to be the most expensive or the costliest, and then you would just continue to pick the next most expensive. And by the end of it, you would have your maximum spanning tree. So the only difference between a minimum spanning tree and finding a maximum spanning tree, you do the exact same algorithm, the exact same steps. You just pick the most expensive instead of the least expensive, but everything else would stay the same. As far as algorithms go, Kruskal's is pretty much as good as it gets compared to everything else we've seen so far. I mean, 1, it's easy to implement. 2, it's efficient. As we increase our vertices and number of edges, the amount of work grows about the same as it would. So if you were looking for an MaxST for a 30-city network, it would maybe, if it took 30 minutes, then finding it for a 60-city network, you'd expect to maybe take about 60 minutes. So it's not as if it grows exponentially. Really, Kruskal's is about as good as it gets. The best part, last but not least, is that Kruskal's algorithm is actually an optimal algorithm. In fact, every time you do it, you are guaranteed to always find a minimum spanning tree. Remember, the only way that we could have that in the previous chapter, for chapter 6, was to use brute force algorithm, which, as you can recall, was not very fun. But the nice part is Kruskal's algorithm is super easy, and it also is an optimal algorithm, and you will always find a minimum spanning tree. So, hopefully you enjoyed that. I know Kruskal's algorithm is probably one of the favorites that I have as far as algorithms go. If you have any questions, let me know. Until next time, guys, have a good rest of your day.